We need some way to get CO2 back into the atmosphere that preferably doesn't involve another snowball Earth. But anyone who tells you that rapid environmental change may be good for you should look back closely on the planet's history. Given a time machine, it would not be wise at all to roll the dice and go back to a random point in geological time. Odds are you'd be dead, and you'd have wasted a nice time machine. The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective on important societal issues.
Produced by Soapbox Media.
The world needs evidence-based public policy now more than ever. Making the right decisions should not be partisan politics. Please help spread The Rational View by going to patron.podbean.com/The Rational View. Together, we can make a better future. Hello, and welcome to another episode of The Rational View. I'm your host, Dr. Al Scott. Have you ever heard someone spouting off on social media that the climate is always changing? Apparently, this carries great weight amongst people who don't want to admit that humans are involved in the accurately predicted warming trend that we're currently experiencing. I just recently encountered someone on social media claiming that the climate is self-correcting and we don't need to worry about how much CO2 we emit. It will take care of itself, like the North Atlantic cod fisheries or the dodo bird. In this episode, I'm going to review the state of our knowledge of past climates on our planet. And please forgive me if I make any mistakes. I'm not an expert, but I do enjoy reading about some of the really cool stuff and sharing it with you. If you like what you're hearing, please press like in your podcast app. I'd love to hear from you on my Facebook group, The Rational View. This episode draws heavily on a nice summary recently published by Elise Cutts in Science News, and I've been going through the sources and trying to put together something that might interest you. So thank you, Elise. Homo sapiens as a species evolved in a rare period between ice ages. The climate we're best adapted for is cold. The poles of the planet are covered in ice. For most of its 4.5 billion year history, our planet was too warm for polar ice. It was not always thus. In the time of the dinosaurs, Antarctica was a steamy jungle and corals blanketed shallow seas, the temperature of bathwater. The Earth's geologic history begins 4.6 billion years ago, the period where the Earth was forming from dust and debris, and the solar accretion disk is termed the Hadean, spanning the range from 4.6 to 4 billion years ago. Why was it called the Hadean? Well, because conditions here were kind of like Hades. It was friggin' hot. It was a magma ocean. How did our solar system come to exist? What caused the sun? Well, from my astrophysics background, I know it's likely that we had a dense molecular cloud in space next to a young star in a young star nebula, and this star went supernova. It sent out a supernova shockwave through our molecular cloud that started it collapsing into a disk that would rotate to become our solar system, and an accretion disk would accrete matter onto the growing young sun. And while it's collapsing, the radioactive debris from the supernova would have seeded our solar system with heavy radioactive nuclei like uranium that remains radioactive today. This disk, this flat disk swirling around the sun of dust and gas and debris, in this disk a small eddy formed, began to swirl and quickly collapsed under its own gravity into a planetesimal that eventually grew to become the Earth. And this happened with all the other planets and also several other protoplanetary planetesimals that never did form planets or left the solar system, were slingshotted out of our solar system by gravity. About 4.5 billion years ago, simulations suggest that a Mars-sized planetesimal that we call Theia slammed into the early Earth. The debris from this collision formed our moon. Well, how do we know this? What's the evidence? Maybe the early Earth was spinning really fast instead and bits spun away. Maybe the Earth gravitationally captured another planetesimal as our moon as it flew by. Well, the second one doesn't seem right because we've done analysis of the isotopes of moon rocks and it closely matches the surface of the Earth, the crust of the Earth. So we believe it it came out of our Earth somehow. Scientists have run thousands of simulations to try to figure out, using supercomputers and our knowledge of gravity and material processes and parameters, how the moon formed. Simulations show that the particular geometry and speed of interaction that forms the moon only happens under very particular rare circumstances. So it's not, a great obvious thing as to how it happened. The moon seems to be a rare occurrence, a large moon such as our own. So far, the only convincing scenarios that have been able to create such a large moon include this particular geometry of interaction between Earth and this Mars-sized impactor we now call Theia. This interaction also explains why the moon is mostly made up of materials with similar composition to the Earth's crust, and it also suggests why the Earth has a particularly large hot metallic core from the metal that was deposited in the core from Theia. In the interaction, when Theia came rumbling into the Earth and a glancing blow, Theia was mostly vaporized, a planetesimal, completely vaporized by the kinetic energy of the explosion. And the Earth itself was melted to a sea of magma, 2,000 degrees surface temperature. The moon coalesced out of the impact debris vapors within a few short hours of the collision. The climate was changed. Yes, the Earth's climate changed, and it wasn't man-made. It was literally Hades, with an estimated surface temperature around 2,000 degrees. And at this time, the heavy metals settled to the core of the Earth. That's why we have a big iron core. And the moon and the Earth began their orbital dance. Tides began kneading the insides. As the moon swings around the Earth, they each stretch in the direction and away from their partner, and this causes heating of the core, and is one reason why we think that the Earth's magnetic field and core remain liquid to this day. This continuous tidal kneading of the center of the Earth. It took several million more years for the surface to cool enough to solidify. Eventually, it cooled enough for water vapor to condense and rain out, flooding the surface to create a great ocean. The Archean eon spanned the time from 4 billion to 2.5 billion years ago, and it's the longest eon in the Earth's history. It's marked by not a lot of interesting things happen. We've discovered rocks that have formed at the start of this period, and these are the oldest rocks we know about on Earth, and they tell the story of the chemical makeup of the early Earth. And we also see the earliest signs of life from this period, where we find evidence of layered stromatolite bacterial mats, which exist today even, and you can go see them oceanside. Archaic life forms that still exist today. Simulations suggest that the surface temperatures in this era ranged from 0 to 40 degrees Celsius. Now, we also understand a bit about stellar life cycles from stellar evolution and looking at stars evolving in other neighborhoods in our galaxy, and we know that the sun would have been about 30% cooler than it is today, back 4 billion years ago. So how was it that the surface of our planet was habitable, 0 to 40 degrees Celsius, with such a much cooler sun? The equilibrium temperature without an atmosphere would have been freezing. Over the lifetime of the sun, it's been putting out more and more heat. How did we stay in this habitable zone for so long? This is one of the mysteries of life, and how we came to be here seems to be a lucky coincidence. The reason the early Earth with the faint young sun was warm enough was greenhouse gases in the atmosphere, lots of CO2 and no oxygen. There was no photosynthesis and no plate tectonics, so there was no way for CO2 in our atmosphere to break down. It would have been a lot like Mars' atmosphere now. Today, rock weathering will trap CO2 into limestone, and plants will trap CO2 into carbonaceous carbohydrates. That wasn't happening back then, so CO2 just built up in the atmosphere. And CO2, as we know, does create a greenhouse effect. So it was able to maintain the temperature of the surface in the liquid water, what they call the Goldilocks zone. Geological studies of ancient soils support high levels of CO2 during this time period. Physical atmospheric simulations suggest that around 20,000 parts per million of CO2 and possibly 1,000 parts per million of methane would have been enough to make it up make up for the faint young sun. As you know, today our CO2 levels is about 420 parts per million, having been about 250 parts per million before we started burning fossil fuels. You might ask why water vapor couldn't have caused this greenhouse effect. We know that water vapor is a strong greenhouse gas. Why do we need CO2? Is this just some sort of hoax, some sort of climatologist hoax? No. If the Earth were cold enough to freeze, there wouldn't have been any significant water vapor. Water doesn't get you out of the problem of a frozen ball of Earth. CO2 doesn't freeze out and can accumulate in the atmosphere, causing warming in the absence of water vapor. Without this enhanced greenhouse blanket, the Earth would have been a frozen ball of ice and life wouldn't have had a chance to emerge. Since this time, Earth's carbon cycle has provided us with something of a geologic thermostat operating over very long periods of time, slowly bringing down the CO2, atmospheric carbon dioxide, which gets transformed into limestone minerals through chemical weathering. So as new plates emerge in the plate tectonics, they weather and absorb CO2 from the atmosphere. This process traps the carbon dioxide in rock, but it doesn't stay trapped forever. Over hundreds of thousands of years, even millions of years, Earth constantly recycles its surface back down into the mantle. The plates will sink down into the mantle and the carbon dioxide will be burned out of the rocks and it'll burp up in volcanoes and come back out on the surface. So this is the carbonaceous cycle that has been maintaining a kind of a constant concentration of carbon dioxide over geological time. The cycle is sensitive to temperature. Chemical weathering speeds up in warm climates and slows down in cold ones. Since the beginning of the Archean, the carbon cycle combined with plate tectonics seems to have maintained the Earth's temperature in a mostly livable range. How do we know this? Well, based on analyzing the genomes of modern organisms and tracing backward to identify shared protein structures in the DNA, we can actually estimate when the last universal common ancestor of all life on Earth arose, and it's estimated based on these processes to be around 4.2 billion years ago. Just the same as the geologic evidence tells us that. We can use radioactive dating of rock crystals to tell us that the oldest rocks on Earth are around 4.1 billion years old. Over the majority of the Earth's history, now this is for the climate denialists, yes, climate does change, but over the majority of the Earth's history, the atmosphere and climate would have killed us. Visitors to this ancient Earth would not recognize it and be dead if they took off their spacesuits. There's no oxygen, no protection from the sun's UV rays on land, no ozone layer. Things changed, though, between 2.4 and 2.1 billion years ago, where they call it the Great Oxidation Event. Halfway through Earth's history, photosynthesis evolved, and photosynthetic single-celled cyanobacteria started changing the atmosphere. Just like an army of little humans, they polluted their environment and over a few 100 million years made it unlivable for the majority of life that had evolved in the previous anoxic conditions. They captured CO2 and pumped out oxygen, bringing the level up to about 1 or 2%. Compared to what it is now, it's like 21% that humans are adapted to. So we still wouldn't have been able to survive in that area. The Earth was still unlivable. How do we know this happened? Well, we can look at sedimentary rock and we see banded iron formation in these ancient seabed rock sediments, evidence of oxygen changing the Earth from a Mars-like reducing an atmosphere to a Earth-like oxidizing one, where we can live and breathe. Oxygen turns dissolved ocean iron into insoluble rust that just precipitates out. So at some point during this transition, near the beginning of the Proterozoic eon, some scientists think that the Earth may have frozen over completely. The CO2 went down enough. Thick sheets of ice may have encased the planet from pole to equator for tens of millions of years. This is controversial in some time periods, but there's even better evidence for snowball Earth, as they call it, having happened more recently in the Neo-Proterozoic era, between 715 and 635 million years ago, after which oxygen levels increased significantly and complex life started to evolve. So the Earth could have been completely iced over, and from space it would have looked like just a white snowball. And the oceans would not have been exchanging air with the atmosphere very much. They would have become somewhat anoxic. Photosynthesis would have slowed or stopped. How do we know? Evidence for snowball Earth occurs at many times in the deep past, consisting of glacial deposits found at tropical latitudes and banded iron sediments thought to be caused by anoxic ocean conditions, being reintroduced to oxygen when the glaciers retreat. These banded iron sediments are often capped by thick deposits of carbonates. What is the theory behind this? How does this happen? Well, we know that albedo, or the reflectivity of the Earth, feedback from advancing white ice sheets decreases the amount of sunlight that the Earth absorbs, cooling the planet. So if glaciers start to emerge, if CO2 gets low enough, you're in an ice age cycle and glaciers get far enough, models show that if they get within about 25 to 30 degrees of the equator, the reflectivity feedback becomes effectively unstoppable, and they just cover the entire Earth in a kilometer of ice. And life on land effectively ends, and we're left with only the deep oceans as viable habitats. They would become anoxic, no more oxygen, shut off from the sun. Luckily for us, it didn't stay this way. Why not? What broke us out of it? Well, over time, volcanoes would have arisen and melted through in certain places, spewing CO2 into the atmosphere. This CO2 would not be absorbed in weathering processes, as there would be no exposed water or land to absorb it. Eventually, CO2 concentrations not being drawn down would become high enough to overcome the albedo, the reflectivity problem. Estimates suggest that atmospheric concentrations of a few percent of CO2, so instead of 400 parts per million, we're talking, 100,000 parts per million, perhaps, would be necessary to initiate surface melting near the equator and provide feedback to offset the albedo losses and initiate glacial melting, switching back to a warmer Earth. When this happens, the CO2 in the atmosphere is quickly trapped in the newly exposed rock formations and weathered into the oceans in runoff, creating a carbonate layer several meters thick in the geological column. And these have been observed. So there is evidence for this happening. It's quite interesting. Photosynthesis rebounded after the snowball Earth about 541 million years ago, pushing oxygen levels up and resulting in the formation of the ozone layer that now protects surface life from damaging UV rays. Prior to the existence of an ozone layer, surface life would have been difficult due to the damaging effects of ultraviolet radiation unimpeded from the sun. This increased oxygen and decreased solar radiation made way for what we call the Ediacaran explosion of complex life forms. First complex life forms in all sorts of different body types evolve. Land habitats opened up. At this point, though, most of the Earth's history is behind us. 4 billion years are down. And only now might it have been possible for humans to just survive on the surface. Any time before that, and it was not enough oxygen. And the temperature could have been freezing, it could have been boiling. Temperatures near the end of the Permian era, about 252 million years ago, were much higher than today. And all the land masses were united in the supercontinent Pangaea. Now, the Permian extinction, which happened at the end of the Permian, is the worst extinction that we know of life forms. Temperatures in the tropics hovered around 50 Celsius, peaking near 73 degrees, creating a sterile desert condition where any life would be cooked before it could survive. Proteins would be denatured. Although forests did flourish in polar regions. The mass extinction at the end of the Permian nearly wiped out all life on Earth. 95% of ocean species and 70% of terrestrial species disappeared. It is thought that the climate change caused this. We know from geologic deposits that 300,000 years before the peak of the extinction, the area known as the Siberian Trap, a volcanic region in Siberia, erupted magma for about 1 million years, covering an area the size of the continental USA and about 50 meters of molten rock, spewing plenty of CO2, which we estimate went from about 425 parts per million, similar to today, up to over 2,500 parts per million. And this is one of the reasons why it was so damn hot. Recent research suggests that the Permian extinction involved two distinct phases of CO2 emissions: a slower initial phase from the Siberian traps, followed by a second, more rapid pulse of CO2 from other sources. And these could have been unexpected feedbacks, potentially including, massive fires, ignition of coal seams, burning forests, dissolved gases bubbling out of the oceans, methane clathrate deposits. All of this happened. The ocean became acidic, and oxygen left. Marine life suffocated. Oxygen breathing fish couldn't survive. Anoxic bacteria then spread out through the oceans and poisoned the water with hydrogen sulfide emissions, like the smell of rotten eggs, that also bubbled up and contaminated the atmosphere. Acid rain fell from the skies. Scientists analyzing bubbles of liquid trapped in salt deposits from this era in the retreating oceans as they dried up give us some evidence of what it was like back then. Now, one of the really interesting things that I've learned that distinguished early Earth from now is that there was nothing alive that could break down lignin once it evolved. Wood, basically, the first woody trees evolved this thing called wood lignin that gives them their structure. Well, there was no microbes that could break this down. Wood from fallen trees wouldn't just rot. It would just sit there. It just accumulated for about 60 million years. Nothing would cause that wood to rot. It just got buried. And what happened is this stored a huge amount of organic carbon in a layer that eventually got compressed into coal and perhaps oil. So this is where our fossil fuel resources come from. 60 million years of trees falling in the forest and nobody hearing them. After the Permian, we call it the Cretaceous period, where our familiar T-Rexes and dinosaurs lived. And in this period, much of the surface became a verdant jungle world with vast swaths of the continents flooded by shallow seas. The average surface temperature was 36 Celsius, still quite hot. A human alive there could not cool off anywhere. This is basically 1 degree below body temperature is the average. Even the polar seas were like a bathtub at 27 degrees Celsius. It was very humid, and this contributed to the greenhouse effect. How did it get so hot? Well, things never really cooled off much after the Permian extinction. Life merely adapted to the new conditions. It took about 50 million years for the base of the food chain to become reestablished after the Permian extinction. New species of plankton began to flourish. CO2 levels remained high, around 2 to 4 times what they are now, we believe, around 1,000 to 2,000 parts per million, keeping things warm while oxygen levels started low and came up as photosynthesis progressed. Methane was also being burped out by microbes at the end of the Permian extinction from that anoxic ocean. The recovery of ecosystems is documented in the fossil record with evidence of a slow return of marine and terrestrial life over millions of years, including the emergence of new groups of organisms and the reestablishment of complex food webs that would thrive in these hot conditions. How do we know CO2 levels were high? Well, various proxies and models support this conclusion. We can measure characteristics of fossilized plant leaves that are related to CO2 concentration. They call it stomatal density. They measure the stomatal density, which in species that have known responses to CO2 that are alive today, that were alive back then. Plants regulate gas exchange with the environment through tiny cellular pores called stomata on their leaves. And the number and density of stomata, the stomatal index, are influenced by the atmospheric CO2 levels. Higher CO2 generally leads to lower stomatal density. They don't need as many pores to bring in the air if the CO2 levels are high. They can get enough carbon dioxide with fewer of these pores, and then they don't dry out as quickly. More pores means more chances of drying out. Towards the end of the Cretaceous, CO2 levels had decreased from their peak down to around 550 to 590 parts per million. Which is where we're heading right now with our burning of fossil fuels. Analyzing isotopic abundances in soils and abundant and plant and animal remains provides more supporting evidence for these high levels of CO2. Once reestablished after the Permian extinction, photosynthesis took off, oxygen levels pushed up, and some people think it pushed up above 30% by analyzing dissolved oxygen in amber deposits or bubbles, various sources. All in all, the Cretaceous would not have been comfortable for humans, especially if we were around a T-Rex. So I've learned from the movies that my son watches. After that, we know what happened. The end of the Cretaceous is marked by a great meteorite strike 66 million years ago that wiped out the dinosaurs, wiped out the terrestrial dinosaurs. Avian dinosaurs survived and became birds. Kind of ruined everyone's day. Fire rained down from the sky. Forests burned. Tsunamis washed up on land. Orbital debris shielded the sun for years afterwards. Acid rain polluted the surface water. The ozone layer would have been temporarily destroyed. 75% of all species went extinct in a matter of years. It took millions of years for ecosystems to reestablish themselves. We can tell from the fossil record. How do we know this happened? Well, we've found the crater that we believe caused it all, and models suggest it was of the right size at Chicxulub in the Mayan Riviera. A global layer of iridium-enriched black soot is found in the geological column at this date, and it caps off the dinosaur-rich fossil layers beneath it. Above this layer, you don't find terrestrial dinosaurs. After the Cretaceous extinction, mammals dominate the fossil record on land, and we see the emergence of our ancestors as CO2 levels are gradually drawn down over millions of years. Eventually, permanent ice caps emerge at the poles, and the planet is swept into a series of ice ages within which emerges our species, Homo sapiens. These ice ages are synchronized to orbital precessions called Milankovitch cycles that were discovered back in the 1970s, actually, which is when news articles trumpeted the oncoming ice age. And these Milankovitch cycles gradually increase and decrease solar illuminance on the Earth over hundreds of thousands of years. Currently, in the Milankovitch cycle, the Earth is heading towards a minimum of irradiance. So we should be heading towards an ice age, except the fact that CO2 levels are rising from 250 parts per million pre-industrially up to about 425 parts per million today. And with it, the climate appears to be warming again, as predicted by scientists back in the 80s. This is not all bad. Plants do flourish with higher CO2 levels. And over time, weathering has been decreasing CO2 levels. So if we want plants to survive for geological periods, we need some way to get CO2 back into the atmosphere that preferably doesn't involve another snowball Earth. But anyone who tells you that rapid environmental change may be good for you should look back closely on the planet's history. Given a time machine, it would not be wise at all to roll the dice and go back to a random point in geological time. Odds are you'd be dead, and you'd have wasted a nice time machine. We, as a species, evolved in a cool period of Earth's history alongside the ecosystems that support us and the plants and animals around us. As we push more CO2 into the atmosphere at breakneck rates compared to previous geological times and climate changes, we risk sudden unexpected feedbacks. We don't want to be like the unhappy cyanogens pumping out oxygen to find that suddenly the world isn't the comfortable blue-green algal paradise it once was. Stay rational. If you'd like to follow up with more in-depth discussions, please come find us on Facebook at The Rational View and join our discussion group. If you like what you're hearing, please consider visiting my Patreon page at patron.podbean.com/therationalview. Thanks for listening.